In this video, we're going to implement both crouching and proning, which is something you might want your character to be able to do if your game contains stealth elements. Many 3D games have some sort of crouching mechanic, and less commonly proning. Their uses can range from staying out of sight to traversing terrain that would otherwise be impassable without it. Though the fundamentals of crouching and proning remain the same between games, implementation can be a challenge for beginners. Today, we'll be adding crouching and proning to our character controller system. The first thing I'm going to do is create a test level. I'll scale the floor to make some room and create a wall by duplicating and scaling a cube, leaving us with 3 holes, one to run, crouch, and prone through. Let's create 2 new inputs inside comp player inputs. Add one input for crouching and another for proning. Inside the inspector, I'll assign crouching to the left control key and assign proning to the X key. With the inputs all set up, we need to change the character controller to account for the 2 new stances. Let's start with creating a public enum called character stances with the values of standing, crouching, and proning. Then declare a private variable called stance that will track which stance we are currently on. Each stance will have their own collider size and speed, so we'll need several more variables to accommodate these properties. Let's create a header called speed. Each speed will be represented by a vector 2. The X component will represent the normal speed of the stance, and the Y component will represent the sprinting speed. Create 3 vector 2 variables called standing speed, crouching speed, and proning speed. Serialize the fields to make them visible in the inspector, and I'll assign them with the default values of 0, 0. Similarly, for the changing collider size, we'll start with creating a header called capsule. Here, we'll use vector 3s to represent the radius, height, and vertical offset of each of the stance's capsule collider. Again, create 3 vector 3s for the standing, crouching, and proning stances, initializing them to vector3.0. Delete run speed and sprint speed, as both of these are accommodated with the new standing speed vector 2. For the rotation sharpness, we'll replace it with 3 new rotation sharpness variables in order to change how fast we turn in each stance, and I'll set each of them to a default value of 10f. Since the run speed, sprint speed, and the rotation sharpness are variable depending on the stance that we're in, we will need 3 new variables to hold their current values. For our collider, create a private capsule collider variable, and in the start, set its value by using getComponent on the object that the script is attached to. We'll also set the run speed to be the standing speed X value, the sprint speed to the standing speed Y, the rotation sharpness to be the standing rotation sharpness, and the current stance to standing. An important part of changing stances is determining if there's enough space. For example, if you are crouching inside a small tunnel, you shouldn't be able to stand up. To do this, we'll use a physics cast to check for the space required, and we'll need a mass for the cast to check against. We could just serialize a layer mass field and set it in the inspector. However, we can make the mask based off the layer that the character belongs to. Right now, the character is on the default layer, and inside the project settings under the physics collision matrix, we can see that the default layer collides with all the other layers. Using this information in bit masking, we'll generate a layer mask in the start function. Create a private layer mask variable called layer mask, and in the start function, create an integer with an initial value of 0. What we're going to do is iterate through the 32 possible layers and check if the GameObject's layer is ignored by them. If the GameObject layer is not ignored, then we'll create a bit mask flagging that layer by shifting 1 I times to the right. This is the one less than I. Then using or equal to add the flag to the mask while preserving the previous flags. Finally, we'll set the layer mask to the mask that we just generated. Additionally, we need to actually be able to request a stance change. You could add the request inside the update function, but I'll be putting it inside the late update function instead. Doing this will allow the physics update to execute first and apply all its changes before we make ours, essentially making stance change checks to be more accurate. We'll make a switch case based on our current stance. If it's standing, then we'll check to see if they entered the crouch or prone key. In either condition, we'll call a new function called requestStanceChange that will be passed the requested stance. We'll do the same for crouching and proning using the appropriate conditions and requested stance. Now, let's create the requestStanceChange function. I'll make this function public to allow other scripts to also request stance changes. As an example, say the user is crouched before mining. We want them to immediately change to the standing stance to properly mine the material, so we'll need to call the requestStanceChange function. We'll first make an early out condition checking if the new stance is the same as the current stance. If yes, then the rest of the logic is ignored and the function will return true. After that, we'll make a switch statement to handle our stance changing. If the user is currently standing and they want to crouch, then we will check if there's room for the crouched collider. It's not really necessary to check if the player can go from standing to crouching because the check will basically always be true when going from a big capsule collider to a smaller one. In any case, we'll do the check anyways. We will call another function called characterOverlap and send it the crouching capsule. This function will determine if there is an overlap between the capsule and other colliders. If there is no overlap, then we will update the current speed, sprint speed, rotation sharpness, and stance of the player to be that of the crouch stance. We will then call setCapsuleDimensions that will modify the dimensions of our capsule size to the crouching capsule, then return true. We'll copy and paste and do the same thing for standing to proning, except we'll use the proning values instead of the crouching ones, and repeat for the other cases. Now, we'll create the missing functions, starting with characterOverlap, which will take a vector 3 that represents the capsule dimensions, and then returns a boolean. We'll use the physics.overlapCapsule non-allocating function to determine the number of overlaps found with our capsule. What we'll need are 2 points that represent the center of the spheres located on each end of the capsule collider, the radius, a buffer to store the results, and the layer mask. We have the layer mask already, so we'll create the buffer as a private array of colliders at the top of the script. I'll allocate 8 elements for this buffer. This length is arbitrary, but it should at least be 2, one to accommodate the player's own collider and one obstruction, and not too long in order to save some memory. We can extract the radius from the vector 3 that was passed in. As for the 2 points, it will be calculated from both the height and the center of the capsule. The height is also extracted from the vector 3. The center is the center of the current capsule collider, substituting the y value with the offset passed in. Before calculating our points, a quick explanation. Right now, our collider has a height of 1.8 from the top to bottom and a radius of 0.25. Reducing the height to 0.5 and below, you'll notice that the capsule doesn't actually get any smaller than the diameter. Therefore, we must take this into account when calculating our points. So, if the height is less than the diameter, then both of our points will be from where we are right now added with the center. Otherwise, we will adjust the 2 points to take into account the height using transform.up. Transform.up is the relative direction we want to offset our points from the center. Since height is the total height with the endpoint spheres included, we divide by 2 and subtract the radius to get the center of each of those spheres, rather than the ends of the capsule. To get the top sphere, we'll add, and to get the bottom sphere, we'll subtract. Now, we have to make sure that our own collider is not considered. We'll create a for loop and iterate through all the colliders. If the current iteration is our own collider, we'll simply subtract 1 from our total number of overlaps. Lastly, we'll return whether or not the number of overlaps is greater than 0. Now we can call this function to see if there is space when you want to change the size of the collider. Next, we need to create our setCapsuleDimension function. All this function will do is change the center, radius, and height of the capsule collider. The calculations are the exact same as the ones inside the characterOverlap. We'll call the set capsule dimensions function in the start, passing in the standing capsule vector 3. Returning to Unity, we have to set our settings in our component. For the speed, x is the normal running speed and y is the sprinting speed. In this case, we'll set our standing speed to 6 and 8, our crouching speed to 2 and 3, and our proning speed to 0.5 and 1. For the capsules, x is the radius, y is the height, and z is a y offset. So for the standing capsule, we'll set it to whatever we have right now. For the crouching capsule, we'll set it to 0.35, 1.35, and 0.675. For proning, we'll set them all to 0.4. These values are just ones that I've experimented with. When you implement your own animations, you'll need to adjust them accordingly to fit those animations and character dimensions. Finally, I'll lower our crouching and proning rotation sharpness, slowing down our turning speed when in either of these stances. Now, if we crouch, we can see the capsule shrinking to the dimensions set in the component. You can now access each of the smaller tunnels, and you'll notice that when inside these smaller tunnels, you can't change into a stance that exceeds the tunnel's size. Now, we need to change the animator to reflect these stances. We'll grab several animations from Mixamo, including idle crouching, crouching to proning, crouching walk forward, idle proning, proning to crouching, and proning move forward. We'll set our import settings. Uncheck import light and camera. Change the animation type to humanoid, change the avatar definition to copy from other avatar, and choose the XSpot avatar as our source. Under the animation tab, each animation will require different settings. Some will have their root transform position Y baked on feet. Some will be looped, some will be baked into pose. If you still have trouble understanding root motion, please read the article in the description below, and we'll do the same thing for all the other animations. Add these animations into the animator controller. Rename our current blend tree as base standing and create two new blend trees called base crouching and base proning. Under the base crouching tree, we will create three motions, one for idle, one for moving forward, and one for moving forward but faster. Uncheck automate threshold. We will set the threshold to be similar to the speed at which they should be moving at. In this case, for the normal crouch forward, we'll set the threshold to 2, and for the faster crouch forward, we'll set it to 3. We'll also increase the speed of the faster crouch speed animation to 1.5. We'll do the same for proning, except the threshold for moving forward and moving forward faster is 0.5 and 1 respectively. Going directly in and out of proning looks weird, so we add extra states to get around this. After adding in the crouch to prone and prone to crouch animations to the controller, duplicate the prone to crouch state and rename it as prone to stand. Do the same for crouch to prone and rename it as stand to prone. Now to add transitions between our states. Add a transition from stand to prone and base proning. Add another transition from prone to stand to base standing and set both the exit time and transition duration to 0.5. Add another transition that goes from crouch to prone to base proning. Lastly, add a transition from prone to crouch to base crouching, and again, change the exit time and transition duration to 0.5. Now we have to code these transitions inside our character controller. If we want to go from standing to proning, we'll set the animator to the stand to prone state and let the transition handle itself. I'll start by making a bunch of constant strings that represent the state names of the states for that transition. Some go through the intermediates, others are direct. Ensure that the strings match the name of your states. From there, inside the request stance change, we'll crossfade between each of these transitions. For standing to crouching, we'll call the crossfade in fixed time function and pass in the stand to crouch constant string as well as the duration of this crossfade, 0.5. Do the same for each of the other transitions, using the appropriate constant string. The duration may vary between each of the transitions, so experiment and use ones that you find suitable. Now we can test this. Upon hitting the crouch or prone key, the character will transition and animate itself to reflect the respective stance. Play around with it more and you'll notice that our transitions to and from the prone state is still a bit wonky, where you can move quickly while the character is in transition. We'll fix this in the next video, but for now we have successfully implemented crouching and proning to our character controller. I hope you are all able to follow along and implement this part into your character controller. It's a bit unfinished, but next week we'll be implementing the fixes needed for proning, as well as creating a custom inspector. Thanks for listening, and I'll see you next time.